Okay, welcome back to Klein's Calculus. We are discussing modeling vertical motion, and we had just talked about how to find velocity and speed of the rock when it's 256 feet above the ground. Two steps. We had to find out when, and then we had to find the velocity. So now let's keep on going with this idea. It might ask, what is the acceleration of the rock at any time during its flight? Well, to find that out, you're just looking for a function. So you say, okay, the velocity at any time is 160 minus 32t. So I'll just take the derivative of that, because the derivative of velocity is acceleration, and I'll end up with negative 32. And that's pretty much it. It just means that we're decelerating. We're going slower at any time during its path. And since we were looking at feet, well, for acceleration, it would be feet per second squared. And when does the rock hit the ground? Well, you've always looked at it as when the position function equals 0. Well, the other thing we can do, because we've already done this, is we can find where v of t equals 0. Because if you recall in part A, we found out that v of t equals 0 when the time equals 5 seconds. So that told us that it took 5 seconds for the rock to reach its maximum point. Well, what comes up must come down. It comes down at the same speed, so it's going to take 5 more seconds for the rock to come down. So if you've already done that, instead of finding where the position function is 0, simply take that 5 seconds times 2, and you'll know the rock was in the air for 10 seconds. It's going to take 10 seconds in all for it to go up and come back down. Okay? So that's all about our vertical motion. Now what about motion along a line? Well, for a second, I'm going to give you one more of these formulas, and I don't think you're going to use it a whole lot, but I want you to know what it's saying in your book. Motion along a line, if you're talking instantaneous velocity, instantaneous rate of change, these all mean the same thing. Velocity with respect to time, the change in position over the change in time. And we could also say, when they look at this, instead of saying the limit as h approaches 0, they're saying the limit as the change in t approaches 0. The change in time. Well, it's f of t, and instead of saying plus h, it's just t time plus the change in time minus f of the change in time over the change in time. So it's the same. This looks different from what you've seen, but it's the same exact thing if you think of the change in time being a small value h. And whether you add it or subtract it isn't really going to make much difference with the small value h. Now let's look at speed. We've talked about velocity being an instantaneous rate of change. Velocity has a sign. If it's positive, the velocity is, the change is accelerating. You're going faster. If it's negative, you're slowing down. Well, you might be asked about speed instead of velocity. And speed is always just the absolute value of velocity. It's that change in position over time, and it's not talking about forward or backward. It's just the change in time, okay? Or the change in your position. Now, when you read a velocity graph, this is a big deal. You probably want to make sure you've got these tips down here, because they're going to show up again and again, and your book doesn't really cover it terribly well as far as saying exactly what's going on. This is a velocity graph. Here we have v of t. It's very similar to figure 3.25 in your book. Okay? Now, when the velocity is 0 at these points, that means the position is not changing. So the particle has stopped. If the velocity is positive, we think of the particle as going to the right, or forward, or up, if it's a weight. When it's negative, we think of the particle as going to the left, or backwards, or down. If it's going towards 0 or towards the x-axis, well, you're going to the left, but you're decelerating, you're slowing down. If you're going away from 0, you're speeding up. Now, even though this is going down, you're still going faster, you're just going left. Here, you can see we're getting towards 0, so we must be slowing down. Here, we're going away from 0, we're speeding up. Okay? When we have a steep slope, like we do right here, well, that means acceleration is larger. Here, where you see this constant slope, there is no acceleration. You're moving at a pretty steady speed. Okay. Here, if we're right on the x-axis, we're not moving at all, okay, because velocity is 0. Remember, the absolute value of the velocity is speed. So if they're asking you about the speed of the particle, you have to decide which is higher, the absolute value of this point or this point, because they're both going to give you a speed. So looking at these things, let's answer some questions. When is the particle at rest? Well, when v of t equals 0. So I would say at t equals 0, and right about t equals 20, and again at t equals 32 to 36. When is the particle moving to the right? When v of t is positive. So we're going to have from 0 to 20, union with 36 to 40. When is the particle moving left? Well, that's going to be when v of t is negative. So we're going to say from 20, t equals 20 to t equals 32. From 20 to 32 on the t-axis. When is the particle moving at a constant speed? That means we need a slope of 0. It's not even changing. So I see that from t equals 4 to 8. Now here you might think it's moving at a constant speed because there's no slope, but it's at 0, so it's not moving at all. When is the particle slowing down? As v of t approaches 0. And that's always moving left to right. So we sped up, we're going along constant, we're slowing down from 8 to 20. 8 to 20. And then we're speeding up again. We're slowing down here. Notice we're approaching 0 from maybe 25 to 32. When is it speeding up? Well, that's as we go away from 0. So as v of t moves away from 0, that's when it speeds up. So here I'm going to look, I'm speeding up from 0 to 4. And then I went constant, slowed down, speeded up from 20 to 22 maybe. And then I slowed down, went along, didn't move for a few seconds, and then I sped up again from 36 to 40. Now the next question, when is the particle at a maximum speed? Well, you've got to think, speed is absolute value, so about negative 8 here, about negative 5 here. So I'd say right here at 24. Well, t equals 24. We're looking at absolute value of v of t. When is it at its maximum velocity? Well, that's got to be a positive number. So now I'm either here or here. This looks like a little bit higher. So I would say at t equals 40. So hopefully this is going to help you out a little bit in this. These are the big ideas to keep track of as we're looking at these graphs. Okay? Now what about derivatives in economics? Because there's another change. Our stock market. For engineers, derivatives are velocity, acceleration. They're concerned with movement. In economics, derivatives are called marginal. It's the rate of change in cost or production. Looking at example 7, if you have C of x equals x cubed minus 6x squared plus 15x, it's the cost in dollars to produce x radiators. So that's our cost function. R of x equals x cubed minus 3x squared plus 12x gives the dollar revenue from selling x radiators. And your profit's going to be the revenue, what you bring in, minus the cost, what it costs you to make them. We want to find the marginal cost when 10 radiators per day are currently produced. Okay? What is the change in the cost if we were to produce one more radiator? That's what we're looking at here. So the marginal cost, well, the first thing I do is I look up here at C and I take the derivative, 3x squared minus 12x plus 15, and then I put in a 10, because that's how many radiators we're currently producing, into the derivative function, and I've got 100, 300 minus 1200, or 120, what am I saying, plus 15. So that's going to be 300 minus 120 is 180 plus 15, $195. So since we're already producing 10, this tells me if I wanted to produce one more, the 11th radiator would cost me $195. Okay? So that's the average, that's the cost of producing one more radiator in a change. Now, if we're looking for the marginal revenue, that would be how much more money we're going to make if we make that one more. I can simply go to my revenue function and write, well, R prime of x equals 3x squared minus 6x plus 12. And then, if I want to find R prime of 10, R prime of 10 equals 3 times 10 squared minus 6 times 10 plus 12. Oh, let's get this here. Put in my 10. And that's going to be 100, 300 minus 60 plus 12. So $252 more. So if I could produce that one more radiator, it would cost me $195, but I would bring in another $252. So that would definitely be worth my while. So hopefully this will help you out some. Look at this, look at the first video, and start your homework, and I'll be glad to help you as needed.